Hi, and welcome to this context bite on thermometers. We are all familiar with thermometers, but you perhaps didn't realise that they work by application of the Zeroth Law of thermodynamics. So, just to remind you of the Zeroth Law, if A is in thermal equilibrium with B and B is in thermal equilibrium with C, then C will be in thermal equilibrium with A. But what does this mean? It basically says that if I have two things which are at the same temperature and I measure the temperature with a thermometer, then the thermometer will read the same value. Or, once calibrated against a known system, I can use a thermometer to measure the temperature of anything I like. So, thermometers are calibrated against known values. Daniel Gabriel Fahrenheit invented the first mercury thermometer in 1714, and he calibrated them against a temperature scale where he set 0 as the temperature of a slurry of equal parts water, water ice and aluminium chloride, which is a eutectic mixture. He then defined the upper part of his scale as the temperature of the blood of a healthy man, 96 degrees Fahrenheit. This put the freezing point of water at 1 atmosphere at 32 and the boiling point at 212 Fahrenheit. These seem unusual numbers, but with 32 steps from 0 to the freezing point of water and 64 from the freezing point of water to the temperature of the blood of a healthy man, the scale divided easily as they are both base 2 values. Anders Celsius invented the Celsius temperature scale initially to have 100 as the freezing point of water and 0 as the boiling point. These values were later flipped to be the temperature scale used in most of the world today. Finally, the Kelvin scale uses the triple point of water as its defining point of 273.16 Kelvin and uses the same size step as the Celsius scale, such as 1 Kelvin difference and 1 degree C difference are the same. These scales do little to tell us how a thermometer works though. Mercury or alcohol thermometers use the fact that the molar volumes of these substances, how much volume is occupied by 1 mole, is temperature dependent. The thermometer design has a very thin tube within the glass through which the liquid is allowed to expand or contract. The thinner the tube, the finer the temperature scale. Some of the mercury thermometers in our labs have scales which can measure as little as 0.005 degrees C temperature differences. Another type of thermometer is a thermocouple. A thermocouple is a device which has two different metals which join to form a junction. A second junction is at a fixed known temperature. A small potential difference occurs between these two junctions depending on the temperature difference between them. Using different metals, we can measure different temperature ranges or have different precision in our instrument. Less precise measurement of temperature can be determined using devices which are near disposable, such as liquid crystal thermometers. These work as liquid crystals are temperature sensitive and due to a phase change at certain temperatures appear black when that temperature is not reached, but coloured when it is. The same principle applies to how colours change in mood rings. My final example of a thermometer has been seen a lot in the COVID-19 pandemic. The temporary artery thermometers have been particularly useful as they are non-invasive and can therefore be used to screen many people without risk of cross-contamination. But the same principle is also used in baking thermometers. These thermometers are recording the infrared output of the black body source and are consequently the only thermometers listed here that don't require thermal equilibrium between the thermometer and the system. I know that I have only quickly covered in the most surface depth how thermometers work, but hopefully now you are aware of the different properties which are temperature dependent and how almost all of them rely on the application of the Zeroth Law of thermodynamics. Thank you for watching this video. If you have any questions, please do not hesitate to contact me.